Okay, what is velocity? In linear motion, what is velocity? Everybody who talks today gets extra credit. For all the time from now till the end of the semester, when you participate in the class, you get extra credit. If you sit there without talking, you don't get anything. Good. What's velocity? Displacement over time, right? Displacement over time. What's the symbol for displacement? Delta x over time. That is when it's moving in a straight line, isn't it? If it is rotating, it's going to be angular velocity. See, instead of linear velocity, you have angular velocity is equal to delta theta over delta t, or theta over t. Same thing. You see the similarity between the two? Because one is moving in a straight line, the other is moving in a circle. What was the unit of this? What's the unit of velocity? Meter per second. What's the unit of angle? Radians. So the unit of this is going to be radians per second. Not a big deal. Now if you look at the screen, you will see the actual definition of what an angle means. Because students many times do not know what an angle is. If you look at that, angle is the length of the arc divided by the radius. Right? So what's the unit of angle? What is length measured in? Meters. What's radius measured in? Meters. So actually, angle is a dimensionless quantity. Actually, angle is not supposed to have a unit. You know what I mean? Meter and meter get cancelled, but we just say it's radians. That's it. So that's the definition of angle. That is why, if you go around the whole circle, you get the circumference, isn't it? What's the formula for circumference? 2 pi r divided by the radius, and you get 2 pi. 2 pi r divided by r is 2 pi, isn't it? So the angle around a point is 2 pi radians. How many degrees is that? 360. So 2 pi radians is 360 degrees. That is what I'm trying to tell you. So if that's the case, 180 degrees is how many radians? Pi radians. Okay. So we need to know how to convert from degrees into radians. What you have to do is just multiply the degrees with 2 pi by 360. And I told you where we got that from. 2 pi radians is 360. 30 degrees. Pi by 6 radian. That's the unit of radian. Okay. Now you can write, because you would have understood by now. 45 degrees is pi by 4, 90 degrees is pi by 2, 180 degrees is pi. Okay, so again, what is acceleration? Acceleration is change in velocity. How do we write that change in velocity? Delta v over delta t, isn't it? And the unit of acceleration is meter per second squared. Don't we know that? Okay. What would be the formula on this side? Well, you do not know what's on the left side. It's going to be angular acceleration. Angular acceleration. Alpha. But tell me what's on the right side. Change in. See, it was velocity here, so it'll be, isn't it? Angular acceleration is a change in the angular velocity divided by the time. See the comparison? Okay, what's going to be the unit of this? See, if it was meter per second squared for this, what's it going to be here? Radians per second squared. Radian per second squared, yes. And don't we have some equations like this? Have you seen an equation like V2 minus V1 is equal to AT? Have you seen this? Yeah, somewhere. So what would be the corresponding equation for that? Omega 2, velocities are replaced by angular velocities. Omega 2 minus omega 1 is equal to alpha t. Okay. Do you know what the king of equations is? On this side, the king. Tell me. We forgot about the king and the queen now. We don't know. Come on.
Change in x equals.
Change in x. Okay. Change in x is equal to. This thing is here. Huh?
V naught times d.
Okay. If we use v1 here, so shall we use the same thing? V naught is v1 here. Remember, initial velocity can be, if you know it, okay, plus 1/2 a t squared. Okay, can you give me the corresponding equation in rotational motion? That you have to think, somebody. What comes in place of delta x? Theta. Because it's angle, isn't it? Okay, it's angle. So delta theta is equal to, go ahead, omega 1. Okay. Omega 1 delta t plus, see, sometimes I write delta t, sometimes I write t. It's the same thing. Delta t or t. Plus 1/2 alpha t squared. And then there is an equation like this, which is like v squared, v2 squared, minus v1 squared is 2 times ax. Anybody remember that? Okay, which would have omega 2 squared minus omega 1 squared is equal to 2 alpha theta. Okay, another look, angular velocity. How do you define angular velocity? Angle described in 1 second. The angle in 1 second. So if theta is the angle and the time taken for the object to go from A to B is t seconds, omega is theta by t. We're going back over this again so you understand. The unit of angular velocity is radians per second. Radians per second. Written like that, rad per second. Okay, there's something called frequency. What do you mean by frequency? How many times? It rotates in 1 second. Frequency. What is the angle in one rotation again?
360.
That's degrees. We want it in radians, 2 pi radians. So if it makes f rotations in 1 second, what's the total angle covered in 1 second? 2 pi times f? Isn't it? Because in each one, the angle. Okay, so we get a new formula there. If f is the frequency, f rotations are made in 1 second, omega is 2 pi times f. F is called the frequency. So that is another way of finding omega. This is a repeat. Angular acceleration, alpha, is d omega by dt. Okay. Look, please write it this way. That is how you write in for the calculus groups, d omega by dt. But it's the same thing, you see that? It just means change in omega by change in time. So if you write it that way, it's not a mistake, but I'm just telling you. And the unit is radians per second squared. Okay, that's all we did, moving along slowly. So we looked at angular velocity, we looked at angular acceleration, and we have to move on. We're going to compare the equations now, because I'm not at all in a hurry. We compared the equations, didn't we? We're going to compare them again, so you see them side by side, and you try to make that relation. Okay, velocity is d by t or x by t, never mind, the unit is meter per second. Omega is radians per second. That makes sense, doesn't it? All right. Second equation. Okay, now I'm using V naught. V is V naught plus AT. You know, V is the final, V naught is the initial, right? And you have the corresponding. Okay, the next, which we call the king of all equations. And the corresponding equation. You have written this, you have written all of this. And then this. E squared is V naught squared plus 2a delta x. Omega 2 squared is omega naught squared plus 2 alpha delta theta. Let me see whether I wrote that. Oh, I did not write the last one. Did you see it? You see that on the board though? Do you see that? Okay. So let's try to get to the bottom of this. But before we do this, I just want to ask you something. Let's come back to reality. If you have a string and at the end of which you have a stone and you rotate it in a circle, come on, visualize that. Is it possible for me to rotate it with a constant angular velocity? Yes, maybe, theoretically. So I'm rotating it with a constant angular speed. You see that? Constant angular speed. I'm going to ask you a very important question now. I'm moving it, like let's say 1 rotation in 1 second. It's always 1 rotation per second, okay? Question is this: is it accelerating?
No.
And that's the obvious answer. That's the answer that I get most of the time. Because students have forgotten. Thomas says yes, come on, go. Why do you say yes?
Velocity is constantly changing direction.
Thank you. Because the velocity is constantly changing direction. Velocity is a vector, so there is an acceleration. We have called this centripetal acceleration. Remember that? And the formula for centripetal acceleration is mass times velocity squared divided by the radius. So even if the object is moving with the same, that was force, centripetal force. Centripetal acceleration would be square of the velocity divided by radius. Thank you. Isn't it? So even if the velocity is constant, there is still an acceleration. What's the direction of that acceleration? Towards the radius. Therefore, it's called either centripetal acceleration or radial acceleration. You got that? Now let's say that I'm going to rotate it this way. I begin slowly and then speed it up. Now you know there's some other kind of acceleration too, isn't it? That is called the tangential acceleration. So if the object is moving around in a circle with constant velocity, still it has an acceleration. What is that called? Centripetal or radial. But if I speed it up, then in addition to the centripetal acceleration, it also has linear acceleration, tangential acceleration. Is that clear enough? That's what we're going to look at. But before that, let's see. I'm trying to relate. I have to see that to see what I did. I can't remember the order. I'm trying to relate linear velocity with angular velocity. Just be with me. Let me ask you some silly questions. If the angular velocity is 0, what's the linear velocity? Definitely 0, isn't it? So if I move it faster, isn't it also covering a greater distance in a small time? Isn't it? So surely this should make sense. Because that means if the angular velocity is bigger, then the linear velocity is also bigger. Isn't it? Okay, I'm going to derive that. It's 2 steps. That's what I'm trying to do. Trying to get the relation between linear velocity and angular velocity. Didn't I define theta as AB by R when we started this class? Didn't I say that angle is length of the arc divided by radius? That's what you see there. Then I made AB the subject. And then we also know that linear velocity is AB by t, distance by time. So I get another formula. Substitute for AB as r theta. And what's theta by t? There you go. So velocity is r omega. 2 steps. Two steps to get that. One substitution, but a very important one. So that's the connection between linear velocity and angular velocity. I already told you what tangential acceleration is, didn't I? I hope you know the difference between tangential acceleration is delta v by delta t. Please write it as delta v by delta t. Don't need that derivation. No, don't write that. That's not for your class. But I just want you to write the last step. What is that? A tan is r times alpha. See that? Tangential acceleration is just write the result, which is what I've underlined. Just write that. A tan is r alpha. Okay, didn't I tell you there are two types of acceleration? Radial acceleration is also called centripetal acceleration. We know that, and I'm just trying to remind you the formula is v squared by r or omega squared r squared by r, which you get it as omega squared times r. I'm giving the directions of both now. Tangential acceleration is along the tangent. Obviously, that is why it's called tangential acceleration. Along the tangent. And radial acceleration is towards the center along the radius. Perfect. The right-hand rule is used to find the direction of angular velocity. The right-hand rule is used to find the direction of angular velocity. Okay, before you continue, let's see all your right hands, please. Put it up with your fingers closed in the direction of rotation. Hold your hand with your fingers in the direction of rotation. Your thumb gives the direction of angular velocity. Is that clear enough? So which means if the object is rotating this way, the angular velocity is up. Got it? But what if the object is rotating in the opposite direction? Then the angular velocity is down. That makes sense? So that's why it's called the right-hand rule. That is what the diagram represents. Look at the red arrows. Is that correct? Yes, it is. Look. Red, up. Green. So that is the right-hand rule. Okay, I'm going to write that down. If speeding up, alpha has the same direction as omega. If slowing down, alpha has opposite direction as omega. So now I've given you the direction of acceleration. Wait a minute. If an object is going to the north, I'm talking about linear motion. If an object is moving to the north and slowing down, what's the direction of its acceleration?
South.
South. See, that's exactly what I said there. If an object is going to the north and slowing down, its acceleration is to the south, right? But what if it's going to the north and speeding up? What's the direction of acceleration?
North.
To the north, right? So speeding up, alpha has the same direction as omega. Slowing down, it has the opposite direction. Okay, again, repetition, torque. Now, from that diagram, you understand what I mean by perpendicular force. Do you see that? Yes. Because the force can be resolved into two components. You only take, so you see the parallel one and the perpendicular one. So calculate the torque. You always take R times the perpendicular component. That's all you need to write from that. Do not write anything else. I will let it roll by because I want this to be complete. Do not write all that. I want it to be complete. So don't write. You don't need the cross product and all that. Okay, but remember the unit of torque is meter Newton or even Newton meter. So you only need the first formula. And then another formula for torque that I told you about in rotational motion. We just got it. Okay. Force is acting there. Alpha increases. If you apply a bigger torque, the angular acceleration will increase, wouldn't it? Okay. You don't need that derivation again. You only need the last part. Not all that stuff. I'm trying to show how you get it. And the last part, for a rigid object, like a disk or a solid sphere, with n particles, I'm trying to get all that and then trying to show how we get that from. And the last one, very important formula, net torque. Don't we write net force all the time? So same way. Net torque is alpha times I, or I times alpha. Isn't that what we've been saying? I is called the rotational inertia. Of course, alpha is angular acceleration. Okay, so with that, you can do problem number 2.